Hello, in this video tutorial we're going to look at AP Physics 1 Workbook, Unit 6, Simple Harmonic Motion. Let's begin. Remember to pause or rewind the video as necessary. Activity A, Forces in Simple Harmonic Motion. Read the scenario along with me. A cart of mass m is attached to an ideal spring that can stretch and compress equally well. The cart and the spring rest on a smooth horizontal track. The cart is pulled to a position A and released. The cart then moves towards position E, where it reverses direction and returns to position A. Using representations. Part A. Show with a sketch a position diagram of how velocity of the cart changes between the points indicated. Okay, so point C represents that equilibrium position. And so what would we expect to see? We would expect to see dots very much spaced out between we pull it all the way to A. Okay, so I'll start with A. And it's going to accelerate from A, which means you will see the dots closer together because the position is changing more for each time interval. So you can see the spacing is getting bigger because the speed is gaining, right? And then all of a sudden, you've reached maximum speed through the equilibrium. And then the block is going to start to decrease the spacing in between and finally slow down to a stop at point E. Part B. The dots below represent the cart at different labeled positions. Draw free body diagrams showing and labeling all forces, not components, exerted on the cart at each labeled position. Draw the relative lengths of all vectors to reflect the relative magnitudes of all forces. You will create one set of sketches for when the cart is moving to the right and a second set for when the cart is moving to the left. Okay, so you can see what this would be when the cart is at point A, point B, point C, point E, and then finally at point E, all the way to the other side. So when the cart is at point A, well, one thing to consider that's true about all these points, and that is the weight of the cart balances the normal force from the surface, and that will never change. So what I'm going to do is I'm going to go ahead and draw a certain amount. I'll just draw, I don't know, I guess. Let's just draw an arrow that's 4 units down. Okay, now that's going to be F sub G. I'm going to draw another arrow 4 units up. There's my normal force. You could write N or you could write F sub N. Either one is fine. Okay, now what I'm going to do, ladies and gentlemen, before we get started, is I'm going to copy that to each and every single one of these other diagrams, because in every single case, the weight of the cart, which is the gravitational force, is going to equal, oops, there we go. The weight from the gravitational force is going to equal the normal force. So I'm just kind of setting that up for each picture just to make the rest of the pictures easier. Because basically what's happening is at part A, you have full spring force, you have full energy, full spring force. And so at part A, I'm going to draw a longer vector for my spring force, F sub S. But at point B, the spring is less stretched, because remember, spring force is equal to kx. So as x decreases, the force should decrease as well. So this one's going to be significantly shorter, right? And then significantly shorter. And then you'll see no force right here. So at point sorry, let me back that up. At point D, point C, we're going to see no force, no arrow, and thus no acceleration. Keep that in mind, right? Because net force equals ma. They point the same way, and if you don't have any net force, you don't have any acceleration, right? At point D, well, now the net force is going to be about as long as this is in B, but going the other way, pointing back towards equilibrium. Okay, and then finally, the spring force of the cart at E would be the same as it is at A, but pointing to the left. When the cart starts moving to the left, in other words, from E back to point A again, it's just going to be exactly what we have right here. Okay, so that's the last thing I'm going to mention here, is that these would be the spring force in each case. Right here, spring force is equal to 0. Here, the spring force is going left. Here, the spring force is going left. Part E and D, again, spring force is going left. Part C, spring force is equal to 0. And then finally, the spring force is going right. Part C, argumentation, claim and evidence. Do the diagrams above indicate whether the cart is moving left or right? Justify your claim with evidence. Free body diagrams don't indicate motion. They do not indicate which way something is moving. So no, the short answer is no. The free body diagrams do not tell whether or not the cart is going to the left or right. They represent the direction of the spring force, and that's not related to the direction the cart is moving. Now, it is related to the direction the cart is accelerating, okay? But acceleration doesn't always happen in the same direction as motion, right? Remember, when we speed up, velocity and acceleration point the same way. So acceleration goes with motion, right? But when we slow down, the velocity vector might be going this way, but the acceleration vector goes against it. Okay, part D. At each point, compare the direction of the net force exerted by the spring on the cart and the cart's displacement from equilibrium when at that position. Note that the question is not asking whether the cart is moving left or right. Use these results to briefly explain why your claim in part C makes sense. Okay, so for part A, position A and B, the net force is going to the right. Okay, so I'm talking about the direction of the net force here. So for position A and B, the direction is easily to the right. Okay, for part C, there is none. Net force is 0. Part D and E, the net force is to the left. Okay, now the second row is the direction of the displacement from equilibrium. So at position A, your position A is positioned to the left of equilibrium. So it's the direction of displacement from equilibrium. So you can see here, A and B are both on the left side of equilibrium, which is right here. D and E are both on the right side. So left, left. None here because equilibrium is x equals 0. Right? This is equilibrium. And then position D and E are both positioned with the displacement to the right of equilibrium. The net force will not point towards equilibrium to bring back the cart to equilibrium. Okay, the net force points towards equilibrium. Okay, so right now equilibrium is positioned to the right, net force points to the right. Equilibrium is to the left, net force points to the left. Okay, and this is done regardless of the way the object is moving. So you can see sometimes it's going left, and notice it's not really always going the same way. AP Physics 1 Workbook, Unit 6, Simple Harmonic Motion. Activity B, Simple Harmonic Motion and Energy Review. Please remember to pause or rewind the video as necessary. Let's begin. A cart of mass m is attached to an ideal spring that can stretch and compress equally well. The natural length of the spring without the cart is at position E. So you can see here, that right there would be the natural length of the spring. The cart and spring rest on a smooth angled track. The cart is pulled to position A and released. The cart then moves towards position E, where it reverses direction again to position A. Okay, so in other words, the cart is pulled all the way down here. It goes all the way to point A, and then all the way to E up at the top, and then back down to A again. One full cycle. So let's go ahead and sketch for part A the energy bar graphs for the cart, spring, earth system at the 5 labeled points. Choose A to be equal to 0 height for gravitational potential energy. What does that mean? A is going to have 0 gravitational potential energy. Since you're starting from rest, you have 0 kinetic energy. That means all the energy we have is going to be, and you can see it from point E right here. Point E, we have all gravitational potential energy, no spring energy or kinetic energy, so the total energy must clearly be 16 joules. Okay, so in every single case, we have to make sure that it all adds up to 16 joules. Right now, we have 0 and 0, so what that tells us is we need to add this up to all the way to the top to 16 joules. I'll make this a little thicker. There we go. There we are. Okay, so we have 16 joules right there. Now, for part B, what's happening is the spring is shorter, so you can see you have less spring energy, so it's shorter. You're getting higher, so you have some potential energy, some gravitational potential, and you're also going faster, so you have some kinetic energy too. Okay, and okay, so to figure out the other parts of the bar chart, let's use the bar charts as a whole, not necessarily just the one at B. Here's what I mean. Trying to figure out how much potential energy should be here. Let's use this as a clue. We start with 0. This is unknown. Now we're at 8. This is unknown. Now we're at 16. Well, let's see. To go from here to here, you jumped 8. To go from here to here to jump 8. That would almost seem like we go about 12 units high in part D and about 4 units high in part B. Because potential energy, we put this over the side, potential energy is proportional to mgh. And what does that mean? Well, potential energy is, m and g are constant. Potential energy is proportional to height. It's linearly proportional to height. So as the height doubles, potential energy doubles. The height triples, potential energy triples. And so you look at your numbers here, 0, 4, 8, 16, 12, 16. The height and thus the potential energy are increasing linearly. Okay, now the rest of it's easy because now we just subtract from 16 to get the rest. So here, if we have 13 total and the total energy was 16, well, that means the remaining must be, draw this a little shorter. Darn it. There we go. Must be 3 units. Now, since we see that the gravitational potential energy increases linearly with height, the spring potential energy will decrease quadratically, because you can see spring potential energy varies with the square of the distance. Well, look at your numbers. We started with 16, 9, it's decreasing quadratically. So 16 would be, what, 4 squared, 3 squared. That means the next part of the pattern would be 2 squared, right? So that would only leave it up to about 4. And those 12 units right there from 16 total energy units would leave 4 remaining units of kinetic energy. Okay, now you see you've got 13 units right there from 16 would leave 3 remaining units. And that should make sense because on the other side of equilibrium, the object's going to start slowing down again at the exact same rate. This was the maximum speed. It was Vmax and it was Kmax. Okay, and then finally, in part E, everything is already established that the total energy is all gravitational potential. The object comes to rest, 0 kinetic energy, and the object is at its natural length, which means x equals 0 and spring potential energy equals 0. So write a short narrative explaining the thought process. Well, we already explained it in terms of the graph, so now let's just write it out in words. At point A, the mechanical energy is all elastic. That means spring potential energy. Since point A was given 0 height, hence 0 gravitational potential energy. And the cart has not yet started moving, so the kinetic energy is also 0. At point B, there will be kinetic energy, gravitational potential energy, and spring potential energy. The gravitational potential energy increases linearly with height, so it will gain 4 units of gravitational potential energy at every marked height. While the potential energy, spring potential energy will decrease quadratically, and the kinetic energy will balance the spring and gravitational potential energy, so the total mechanical energy will always be 16 units. In other words, kinetic energy is the last one you find. At point C, there will be kinetic energy, gravitational potential energy, and spring energy. At point D, there will be kinetic energy, gravitational, and spring potential energy. And at point E, there will only be gravitational potential energy since the cart has come to rest, and this is the original equilibrium position of the spring. Okay, no need to write anything here as we said everything we need to say right here. Part C. Do the energy bar charts depend on whether the cart is moving left, that means down the track, or right, up the track? No. There is the same change in energy in each case, regardless of whether the cart is moving up or down the track. Part D. As the cart moves from A to E, the total energy of the system should be the same at each labeled point. Explain why this is the case. If your energy bar charts do not show this, then make corrections to your bar chart. Well, the reason why, and this is conservation of energy. Okay, and why does conservation of energy work? Because there are no external forces acting on the system. No external forces doing work. So if there's no external forces doing work, that means the energy within the system is constant or conserved. And a loss in one form of energy becomes a gain in another. Part E. As the cart moves from A to E, the gravitational potential energy should increase by the same amount between each labeled point. Explain why this is the case. If your energy bar chart does not show this, then make the corrections to your bar chart. The gravitational potential energy, again, we stated this earlier, is directly proportional to height. So as height increases, gravitational potential energy of the Earth cart system will increase directly. Part F. As the cart moves from E to A, that means down the incline, the spring potential energy should increase quadratically between each labeled point. Explain why this is. If your energy bar chart does not show this relationship, make the corrections to your bar chart. Again, spring potential energy is equal to 1/2 kx squared. So you can see spring potential energy is proportional to the square of the x, not just x. So that means every time the spring potential energy will increase by a factor of x squared. AP Physics 1 Workbook, Unit 6, Simple Harmonic Motion. Activity C, Equations of Motion for Simple Harmonic Motion. Please remember to pause or rewind the video as necessary. Let's begin. In this scenario, we have a cart of mass m resting on a smooth surface is attached to an ideal spring. The cart is displaced to the right a distance delta x from equilibrium and released. Well, while the cart oscillates around the equilibrium position, a motion detector collects data to make the following graph of position as a function of time. Using the graph, determine the following. Well, we have to determine t, the period, f, the frequency, omega, time or times of maximum positive velocity, the times of maximum negative velocity, times when velocity is 0, time or times of maximum positive acceleration, maximum negative acceleration, and when the acceleration is 0. Okay. Now, what we're going to do, we're going to identify these times, but up above here, we're going to write some notes as to when these places would occur. We'll also actually make some notes on the graph itself where these places would occur, because that will actually help out a lot. Okay, so, excuse me. Okay, so one of the first things I notice is that the amplitude is equal to 4 meters. That's going to become in handy. Okay, the period, we can see it goes from the top of the crest here to the top of the next crest, and that happens to be, 4 seconds? Okay, so the period is 4 seconds. Now the frequency, well, that's the inverse of the period. So we're going to go, 1 over t, which would be 1/4 or 0.25 seconds. 0.25 cycles per second, or 0.25 hertz. Okay, the omega is 2 pi over the period. So if I go 2 pi over 4, that's going to reduce to pi over 2 radians per second. Okay, so max, let's work this out. Max velocity, okay, we'll work out positive and negative in a minute, but max velocity occurs at the equilibrium position. Okay, so max velocity. So equilibrium, let's start there. That would be 1, 3, and 5 seconds. Now, not all of those are going to be, we're not going to put 1 through 5 seconds for each one because, for instance, this here has a negative slope. Therefore, this is negative velocity. This right here has a positive slope. This would be positive velocity. This here has a negative slope. This would be negative velocity. So the only time of positive velocity would be 3 seconds, whereas the times of negative maximum velocity would be 1 second and 5 seconds. Okay, times of zero velocity. Well, zero velocity occurs at the amplitude. So at the amplitude right here and right here. Okay, and right here too. Right here and right here. Okay, velocity equals 0 at the amplitude. So when does velocity equal 0? It equals 0 at 0 seconds, at 0, 2, 4, and 6 seconds. Okay. All right. Now, the next one is times of maximum positive acceleration. Well, that's going to occur, first of all, it's going to occur at amplitude. Okay. And then maximum negative acceleration is also going to occur at amplitude. Now, time of positive maximum acceleration is going to occur when you are speeding up, going up. Okay, so speeding up, and this wasn't going up, but going back towards equilibrium. So speeding up, going, how about forward? There we go, speeding up, going forward. Whereas times of maximum negative acceleration would be those times where you're speeding up, but you're going backward or you're going in a negative direction. Okay, so this would be speeding up going forward. This would be speeding up going backwards. So the concave uphill, you're speeding up. With positive slope, you're going forward velocity. Here we're going from steep to, from flat to steep, so we're speeding up, but with negative slopes, backward, negative velocity. Okay, so I'm seeing two of those. I'm seeing steep or flat to steep, so here and here, and then both of these two. So I'm seeing times of maximum positive acceleration at 2 and 6 seconds, right here and right here, basically at the bottom of the sinusoidal curve. And I'm seeing at 0 and 4 seconds, times of maximum negative acceleration. Now, times of zero acceleration, that's easy. That's going to be at equilibrium, so 1, 3, 5. Okay, remember from math class that the equation to describe a cosine wave is x equals a cosine of 2 pi f times t, where a is the amplitude, f is the frequency, and x is the position of the function, is the position as a function of time t. In terms of the data you collected, write an equation for the position of the cart. So basically, we're just going to substitute. We're going to substitute all those numbers. So we're going to put 4 for a, so 4 cosine And then what I'm going to do is I'm going to go 2 pi times 1/4. Okay, another way to write this would be 2 pi f is omega, so omega t. And omega t is already pi over 2. So we could write it that way too. Right, that's going to be 4 cosine of pi over 2t. Another group of students collected the following data from their motion sensor. What is one possible explanation for the differences in the graph created by the two groups? Well, it's pretty easy because you can see at time equals 0, this graph starts at the amplitude position. So that means they released the cart. When they released the cart from rest is when they started collecting data from the motion detector. In other words, when the car was at rest at the amplitude. But here, the car has maximum speed through equilibrium. So what I think probably happened is if we draw a picture of the cart, here's the spring, there's the equilibrium position, and there's the cart. What had probably happened is the cart was released and got to the equilibrium position right here when the motion detector was turned on. So I think the motion detector was probably not turned on until it got to the equilibrium position. Okay, so yeah, they probably started their timer as the cart was passing through equilibrium instead of when it was at maximum positive amplitude. A little typo there. Okay, so write an equation that describes the position versus time of the second group's cart. Well, that's a sinusoidal function. That's a sine function, not a cosine function. So x is equal to a sine omega t. Remember where a was 4 and omega was pi over 2. So x equals 4 sine pi over 2 times t. Part E. The second group repeated their procedure, thinking perhaps if they added mass to the cart, it would help their analysis. On the graph in part C above, sketch the position versus time graph of what the cart would look like with a mass of 4m. So if we quadruple the mass, what's going to happen? Okay. If we go and look at our equation, t equals 2 pi times the square root of m over k, the spring constant. The spring is the same. Nothing has changed, but we're saying we're going to make the mass 4 times heavier. What this means is the period of the oscillator is directly proportional to the square root of the mass, but you're quadrupling the mass. So t prime, or t nu, square root of 4 equals 2. What this means is 4 times the mass relates to doubling the period. Okay, the period was 4 seconds. So now the period, right, is 8 seconds. Let's go up to the graph and make that. All right, so now the only way you're going to be able to make that is you're going to have the exact same graph, but it's going to be stretched out. So in other words, instead of going up and down like this, where you're going up, down, and then you're returning at 4 seconds, you're only going to go up, down at 4 seconds, and then at 6 seconds, you're kind of ready to come back up again. But you can see there's just not enough. If there was 7, 8, you would probably see it would return to one full cycle over here. But that's good enough for now. AP Physics Workbook, Unit 6, Simple Harmonic Motion. Activity D, Measuring Spring Constants. Please remember to pause or rewind the video as necessary. Let's begin. In this scenario, Angela and Blake are given a spring and asked to determine its spring or force constant. Both students are given a stand on which the spring may be attached, different known masses that can be attached to the spring, and an electronic balance. Angela, in addition to the equipment above, is given a meter stick, but has no access to a stopwatch or any other way to measure time. Explain how she can make the measurements and how those measurements can be used to calculate the spring constant. Okay, let's kind of draw a picture of that. Basically, you have the spring itself with nothing hanging on it. This is before. Okay, and we've done this lab. This is our Hooke's Law lab. And then when you add mass, okay, what happens is the weight going down balances your spring force, which is equal to K times X going up. All right, so let's take a look how that could be written up. Hang the spring vertically and measure the initial equilibrium length, L naught. Okay, so that would be this phase right here. Hang known mass on the spring to stretch it to a new length, L. New length L is now. Repeat with different masses to reduce the error. So the only data that's taken is simply putting known masses and simply measuring the stretch. Just measure how far it stretches. Okay, now how can we calculate K? Well, first of all, we calculate the length of the change in the length of the spring by taking the whole length, the whole new stretch, and subtracting the initial, and we're going to get this value here, which is our displacement. Well, we can call it delta L or delta X, whichever, doesn't matter. But it's the displacement of the spring. Calculate the weight of each mass, which would be your mg right here. And then finally, you're going to graph each of the mass versus the change in the spring. So we're going to be graphing the mass versus delta L. And when you get a straight line through the linear data, and the slope, right, is going to equal K, the spring constant. So that's one way to do it. That's one way to do it. And if you're not sure where we're coming up with this, just remember, take the original equation. Let me back this up a minute. The original equation was spring force equals the weight. So in other words, Kx equals mg. Go one at a time. Spring constant, K is a constant. X is a variable because you measured it over and over again. Mass is a constant, and mass changes, excuse me, mass is a variable, and a G is a constant. So what we're doing is we're getting divided by X, okay, and what we'll do is we'll just multiply this constant times G, and so what we get is we get mg over X, which is the distance you're stretching it, right, is equal to K, which mg is your rise. So the weight of each mass, mg. That's your rise over your run, right? And that's going to be mg over x, which is k. And since rise over run is slope, that means k, the spring constant, is your slope. In addition to the equipment above, Blake is given a stopwatch, but has no access to a meter stick or any other way of measuring distance. Explain how he can make the measurements and how those measurements can be used to calculate the spring constant. Well, Angela used Hooke's law, right, which tells us that the restoring force is directly proportional to the displacement from equilibrium, but opposite in direction. And it's Hooke's law, and quite honestly, Newton's first law, that we're equating, right, those forces that are in opposite directions. Well, Blake, on the other hand, is going to use a method where we take our mass and we let it hang. And there's our equilibrium position. This is before. Then what happens is you pull that down or hang it above the equilibrium position, and it's going to oscillate up and down from here to here. Okay, it's going to oscillate up and down on either side of that equilibrium position. And what we can do is we can measure the time for 10 cycles, which will allow us to get the period, the time for one cycle. Right? Then we can use our equation, t equals 2 pi times the square root of m over k, right? And that will help us create a graph that will help us solve for k that way. So we're using the period of an oscillating mass. Okay, that's what Blake is doing. So let's re-describe those measurements again. Okay, we're going to hang the mass vertically to basically stretch it. We're going to pull it down and measure the time it takes to complete 10 cycles. We'll call this T10. We'll divide by 10 to get the time for one cycle, or the period of oscillation, T. And it's very important to include this last sentence. Repeat with different masses to reduce error. In this case, repeat with several masses to reduce error. So basically, repeat with other trials. What are those other trials? Hanging more mass on the end of it, right? Okay, now the calculations. Since period squared is proportional to mass in the spring, Blake should graph t squared versus the mass. Okay, let's see how we came up with that. First, we start with the equation. Whoops, I erased it. We start with the equation right here. Okay, I want to write it down here. So t equals 2 pi times the square root of m over k. Now, the first thing we do is we're going to square both sides. Okay, and we're going to rewrite it. We get t squared equals 4 pi squared m over k. Let's go one at a time. The period is a variable, mass is a variable, 4 pi is a constant, and c is a constant. So what I'm going to do is I'm going to get my variables together. I'm going to divide both sides by mass, like that. All right, and if I rewrite this, I get t squared over the mass equals, and what's left over is 4 pi squared over k. But t squared is your rise, right? And mass is your run, which means this is going to be your equal to the slope of your best fit line. So ultimately, you're graphing t squared on one axis, mass on the other. You're going to get that nice linear data. And the slope is equal to 4 pi squared over k. Now, to solve for k, you would just inverse that, and that's how you'd solve for k. Part C. Now suppose both students and the classroom, including all equipment, are transported to another planet where the acceleration due to gravity is greater than Earth. For each student, List the measurements taken above, not calculated, and what would be different on the new planet. Well, for Angela's, let's remember what Angela and Blake did. Angela was about hanging mass. Now, if you go, the mass doesn't change. But remember what happened. We said that the weight going down is going to balance the spring force, kx, going up. So if you go to another planet where the acceleration due to gravity is greater, you're going to pull it more, right? Which means x is going to be greater. So the delta x, the displacement, is going to be different because the gravity is going to be different, right? And that's essentially what delta L, I should say, we can call it x or delta L, whichever one. Basically this right here. It's going to be different because the acceleration due to gravity over here is different, which means the weight pulling on it's going to be different. Okay, now Blake was using the oscillating mass method, and the period of an oscillating mass is proportional to the mass itself, which does not change when you go to another planet, and the spring constant K, which is kept the same. Therefore, Blake's should experience no change or no effect. Gravity does not have an effect on the period of a pendulum. Blake's measurements will be unaffected by the different acceleration due to gravity, since the period of a spring is independent of the acceleration due to gravity. Okay, part D. Which student, or both, or neither, will obtain a different value for the spring constant? In a clear, coherent paragraph length response, explain your reasoning. Neither student will obtain a different value for the spring constant. For Angela, K is equal to spring force over X. On the new planet, the force of the mass would be greater, making the force from the spring stronger and stretch the spring farther. The greater the stretch is proportional to the greater force. Okay, so basically what we're saying is this will be greater, but they're both going to be greater by the same amount, which means K is not going to end up changing at all. Blake, the period is independent of the acceleration due to gravity, right? The period of the mass spring system depends only on the mass and the spring constant, neither of which change. A greater gravitational force does not change the measurement for K. The spring constant will be the same.